Now, what if you were asked to solve this system algebraically instead? So we can use the method of substitution to solve a system that includes both a quadratic equation and a linear equation. So our quadratic equation was y equals x squared minus 3x minus 20, and our linear equation is y equals negative x minus 5. So you'll notice that both of these equations are set equal to y, which means if the left side of each equation is y, that means that the right side of each equation must be equal to each other. Because if y equals x squared minus 3x minus 20, and we know that y is equal to negative x minus 5, we know that x squared minus 3x minus 20 must be equal to negative x minus 5. Now this is a quadratic equation that we can solve. It needs to equal 0, so we would add x to each side, and we would add 5 to each side. So x squared minus 2x minus 15 is equal to 0. So we want to find the solutions of this quadratic equation. Now, you learned many ways to do that in the last unit. You could factor, you could use completing the square, you could use quadratic formula. Really, your two best options are either factoring or your quadratic formula. I'm going to factor because I notice here that the two numbers that multiply together to equal negative 15 and add together to equal negative 2 are negative 5 and positive 3. So the two factors are x minus 5 and x plus 3, which means to find my two solutions, I have x minus 5 is equal to 0 and x plus 3 is equal to 0. So x is going to equal 5 and x is going to equal negative 3. Because we were able to find two values of x when we solved using substitution, that means there are two solutions to this system. To find those solutions, remember solutions are written as ordered pairs. To find those, we need to take our x values and find the corresponding y values. So again, our two solutions for x were 5 and negative 3. So you're going to pick one of your equations from the original problem and you're going to substitute the x value in. I am going to pick my most simple equation and I am going to use the linear equation. So y is equal to negative x minus 5, and if x is 5, that means y is equal to negative 5 minus 5. So the y value that corresponds with 5 would be negative 10. So my first solution is the ordered pair 5, negative 10. We're going to do the same thing for our x value of negative 3. Y is equal to negative x minus 5. So y is equal to the opposite of negative 3 minus 5, which would be 3 minus 5. So y is equal to negative 2. So our second solution is the ordered pair negative 3, negative 2. That means that if I were to graph this system, the line and the parabola would be intersecting at 2 points, and those 2 points would be 5, negative 10, and negative 3, negative 2. Now, if you wanted to check your solutions here, one way that you could do that is you could take these solutions and you could substitute them back into the original problems. If you substituted 5, negative 10 into either of these equations, you would end up with a true statement. Same thing for our second solution. If I substituted into either the linear or the quadratic equation, that ordered pair is going to satisfy both of those equations. Now, all the systems that we have looked at thus far have had two variables. We've had an x variable and a y variable that we have solved for. The last part of this section is to solve a system of equations that is in 3 variables. So we have x, and we have y, and we have z that are unknown. To do that, we are going to use the elimination and substitution that we have talked about in solving these systems. Now, a system of equations in 3 variables cannot be solved using graphing at this time. You will have to use an algebraic method. So, to start out, the first thing that I do when solving a system in 3 variables is I label my equations. So, this would be equation 1, this is equation 2, and equation 3. Our first step here is going to be to try to eliminate one of our 3 variables. And we are going to use the algebraic method of elimination to do so. So if I look at these 3 equations, I'm going to notice that in equations 2 and 3, the y values are opposite each other. In equation 2, my y value is negative 5y, and in equation 3, my y value is positive 5y, which means in using the method of elimination to solve a system using those 2 equations, my y is going to cancel. So I'm going to pull over equation 2 and equation 3, and we are going to use elimination to eliminate the y variable in these 2 equations. Alrighty, remember elimination is where we add vertically. So we are going to add together our x column, our y column, our z column, and our constant column. So negative 5x plus 2x is negative 3x. Negative 5y plus 5y cancels. 5z minus or plus negative 3z, same thing, is plus 2z equals 5 plus negative 10, or 5 minus 10 is negative 5. This is an equation that resulted in using elimination on equations 2 and 3. I am going to label that equation 4. All right, let's go back to our original 3 equations. Our next step is going to be to pick 2 different equations, so not equations 2 and 3 again, but we need to pick 2 different equations to again cancel out the y variable. So I want you to notice that equation 1 and equation 3 also have y terms that are opposites, negative 5y in equation 1 and positive 5y in equation 3. So the next thing that I'm going to do is I'm going to pull out equations 1 and 3 over here on the right. And again, we are going to use the elimination method to cancel out our y term in these 2 equations. So we are adding these 2 equations together. Negative x, so that's negative 1x, plus 2x is 1x, or just x. Negative 5y and 5y cancel. 1z plus negative 3z, or 1 minus 3, would be minus 2z. And that is equal to 17 plus negative 10, which would be 7. We will call this equation equation 5. Now you will notice that equations 4 and 5 both contain the variables x and z. The next thing we are going to do is we are going to use elimination yet again on equations 4 and 5. I want you to notice that the z term in equation 4 and the z term in equation 5 are opposites. So when I use elimination, my z variable is going to cancel. So I am going to stack equation 4 and equation 5. And we are going to add those equations together. Negative 3x plus 1x is negative 2x. The z's cancel, equals positive 2. Divide by negative 2, we get x is equal to negative 1. We have found one of our 3 solutions. Now, the solution to a system of equations in 3 variables is written as an ordered triple. So if x is negative 1, my solution would go right here. Now that we know that x is equal to negative 1, we will figure out what z is equal to. So notice that equations 4 and 5, again, are written in terms of just x and z. So now that I've found one of my values, I am going to substitute it into either equation 4 or 5. It doesn't matter which one you choose. I am going to go with equation 4. So I'm taking equation 4, which was negative 3x plus 2z equals negative 5. And I'm going to substitute negative 1 in place of x. I'm going to move this over here to continue. So negative 3 times negative 1 would be 3 plus 2z equals negative 5. Subtract 3 from each side, so 2z is equal to negative 8. Divide by 2, z would be equal to negative 4. So the third piece of my solution is negative 4. The last thing we need to find is y. Now, y only exists in the equations 1, 2, and 3. So you're going to pick equation 1, 2, or 3. It does not matter which equation you pick. And you're going to substitute your known values for x and z. I am going to use equation 1. So again, equation 1 was negative x minus 5y plus z equals 17. X was negative 1, so the opposite of negative 1 minus 5y plus z, which is negative 4, so minus 4 equals 17. The opposite of negative 1 here is just 1. So we now have negative 5y minus 3 equals 17. So negative 5y, add the 3 equals 20. And y is equal to negative 4. So our ordered triplet, or ordered triple, for this equation is negative 1, negative 4, and negative 4. That is the solution to this system of equations in 3 variables.